Hi, everybody. I hope you're having a good day. This is a recording for our lesson from May 17th and May 18th, where we are looking at polar curves. So we have a warm-up here, just a little multiple choice warm-up. Which of the following represents the polar point 4 pi over 2 in rectangular form? So I'd like you to go ahead and take a moment to try that. All right, so I'm hoping you've tried it and given it a shot. The result is that, I think the animation got a little bit funny over here, but the result is that we should end up with the XY coordinates 0, 4, right? So in polar form, 4 pi over 2 means that our radius is 4 and our angle is pi over 2. So basically we would go out 4 on the radius and then up to pi over 2. So the rectangular coordinate point then would be 0, 4. Okay, so what we're going to do today is we're going to learn how to recognize polar graphs, describe properties of polar graphs, and write equations of polar graphs. We've got a warm-up, a Desmos activity, and then summary and check for understanding. We do have week 5 homework and formative, and just remember weeks 1, 2, and 3 can still be made up if you were late with them, and then week 4 assignments are due this coming Wednesday, the 19th. Okay, so just a reminder of some of the vocabulary that we use with polar graphs. So on our rectangular grid, we call 0, 0 the origin. In a polar grid, we call that the pole. that's kind of how polar grids come to be. So the center or the origin that we think about in the Cartesian plane, the equivalent in polar world is the pole. The positive x-axis is equivalent to what we call the polar axis. So sometimes we will look at a polar curve and say, oh, that curve is symmetrical to the line theta equals pi over 2, or symmetrical to the polar axis. The polar axis is basically the positive x-axis, and then the y-axis is theta equals pi over 2. These are some of the graphs we explored and discovered a little bit last week, but didn't really solidify. So we had a circle, a cardioid, a limacon, an inner loop limacon, and then these are the equations that go along with them. So I'm not going to spend a lot of time just like showing you that today. We're going to really more look at it by discovery, but I know that discovery doesn't work the best for everybody, so I want you to have those resources. And then here is a little bit more of that. We've got this is called a lemniscate. We're not really going to study these, but we've got rose curves, right, with the petals that are determined by the number in between the inside the argument before the angle. So a cosine n theta, a sine n theta. So these are some of the curves that we're going to be working with. We're going to spend most of our time on circles, cardioids, which are special types of limacons and then curve, and then rose curves today. But these are the common types of graphs that we deal with. Okay, let's go ahead and get into the polar graph exploration. And finishing this Desmos activity is going to count as your homework for this week. It'll be 10 points. So depending on what period you're in, you would go to the slides from this week and click on whichever period applies to you, right? So if you're period 2, you go here and so forth. And we're going to go ahead and get into the lesson. All right. So again, you should be kind of, if you're watching this, you're not in class. So if you're watching this, you're going to basically self-pace yourself through this activity, but I'm just going to guide you through it a little bit. So for polar graphing, right, you're going to explore the slider B, right? You have B cosine theta, B sine theta, and play around with it a little bit, okay? And then you'll figure out, you'll type in here, what's B all about, right? What did you notice was happening as you moved the slider B? So you'll do that. And then now, having discussed what happens with the slider, we know that B moves the diameter of the circle right? And so with sine, we see that here sine is red and cosine is blue. So with sine, we see that it's symmetrical with theta equals pi over 2, but with cosine, symmetrical about the pole. Okay, so that's interesting. And then if I have a negative b, my cosine graph kind of flips. It's still symmetrical along the x-axis or the pole, and then the y graph is still symmetrical about pi over 2 or the y-axis, but now they're on the negative side. Right? So if we're supposed to write an equation here, I would say this equation, the diameter is 3. I would say r equals 3 cosine of theta. And look how nice that is. If you type THETA, it's there, right? Okay. How about this one using, this should actually be sine. So I'll fix that for the slides. But using sine, this should be r equals, now we have 3 sine of theta. Okay. All right, so 3 is basically your circle's diameter, and then cosine dictates whether it's along the x-axis, sine dictates whether it's along the y-axis. I can edit it right now, can I? All right. How about some differences? So what are some differences? You might say, well, cosine is symmetrical across the pole, whereas sine is symmetrical across pi over 2. But they're both circles. They're both they both have a point on the origin or the pole. So you can think about what you notice about the similarities and differences. All right, so some roses, and we discovered this a little bit last time, right? We knew that if we have r equals b cosine n theta or r equals b sine n theta, b is still controlling the diameter of each little petal or leaf or loop, right? But what n is controlling is the number of loops. So if we have an n of 1, that's just a circle. 2, we have 4 loops. 3, 3 loops. 4, 8 loops. 5, 5 loops. 6, 12 loops, and so on and so forth. And we can animate, right? We could just, play it and let it go, or we could slide it, however you like. And then we'll look at sine equations. So how do sine equations look? Right, so we can animate that, animate both of these, and see what we see. I'm gonna do that. I think I can't. If I go back, get back in there. Okay, yeah, there we go. We're good. Okay, so here's where you would type in some differences. What are some differences between the cosine rose graphs and the sine rose graphs? How are they the same? How are they different? And since you're watching this at home and not in class, what I would like you to understand is that the cosine graphs always have a loop that is symmetrical to the pole. So this blue graph is the cosine graph, and the red graph is the sine graph. So the sine graph is actually a rotation, a counterclockwise rotation of the sine graph. So I just want you to understand that. The sine graph has the same size, same shape. It's a counterclockwise rotation. What happens to your graph as n changes? You notice the number of petals is dependent on n. Write an equation for this graph in terms of r and theta. And I would say the diameter is 5, so 5 cosine of, and then 5 theta, right? R equals 5 cosine 5 theta. So when you have an odd number of petals, your n is just that. If you have an even number of petals, it would be twice that. So let's look at the next slide. Here we would have, this looks like a radius of 3. So r equals 3 cosine, there are 3 petals, so 3 theta, 3 cosine 3 theta. Here we've got, again, this is going to be cosine because we have a petal that's symmetrical about the pole. So r equals, we've got a radius of 4 cosine of 2 theta because that's 4 loops, right? So if we have 4 loops, our n here is going to be half as much because we always have twice, when our n is even, we always have twice as many petals as the n parameter gives us. All right, and for this one, I would say, so let's see, we've got a radius of this looks to be 4 as well. So we've got R, but it's a counterclockwise rotation, right? So R equals 4 sine of 2 theta, right? 4 sine of 2 theta. All right, so there are a couple more you can practice on your own and see what you get. And now we've got, this is a joke, you have my cardioid, right? Because cardioid is about your hearts, right? So you have my cardioid. So let's play with the sliders here. So now we have a different format, A plus B cosine theta. So we'll move A around, we've got A of 1 and 5 and 7. Okay, so A still seems like it affects this diameter, right? It's still kind of making the diameter of whatever we want to call this bigger, right? So it's like a vertical stretch, or not a vertical stretch, a dilation. B, what is B doing? Well, it looks like B is moving this shape left and right. So that's interesting. Okay, so A is kind of a little bit of a diameter and B is moving it left and right. So this says set B to 4 and animate A. We'll do this again, going back and forth. And then we've done that, and then we'll set A to 3 and animate B. All right. So it looks like A is kind of controlling diameter and B is kind of controlling how it's oriented to the pole, okay? How about when you have a loop? Do we notice that the loops only happen, oh, this is still animated. The loops only happen when B is bigger than the absolute value of B is bigger than A. So if you have a negative A and like a B that is more negative, we have a loop. If they're the same, we have this special heart, this cardioid, right? So if B is less than A, I'm sorry, if B is greater than A, we have a little bit of a loop, right? Otherwise, if B is smaller than A, okay, let me try to make this a little bit more clear. So say we have A of 4 and we have a B of 2. Right. So no loop, right? No loop yet. And then when they're the same, we have that heart shape, that little point, right? But then when B gets bigger, we have a loop. Okay. When B gets bigger, we have a loop. Let's look at a negative A. Okay, so then we have negative. So same thing, how B, the absolute value of B gets bigger than A, we get a loop. Then once the absolute value of B is less than A, we don't get a loop anymore. It's just a little dimple. All right, so can we write an equation in terms of R and theta for this graph, right? So we have that our radius, or not radius, but diameter is about 5. Our dimple goes down to 1. So what do you think? How would we write the equation of that graph? All right, so we can see that from the dimple, or from the sort of where the origin goes, we're out 5, right? So we're gonna have R equals A plus B cosine theta, and we just have to figure out what A and B are. Okay, so because we're going out to 5 from 0 to 5, A plus B has to equal 5. Excuse me, right? But how do we know what A is going to be and what B is going to be, right? So what we're gonna look at is, well, if A plus B is 5, and we know that this little dimple here is only 1 space, what are 2 numbers that would add up to 5, right? That would only have a difference of 1. And that would have to be 2 and 3. 2 and 3. So 2 plus 3 cosine of theta is going to be our equation for that. All right, so I'll leave you to write this one. Since it's a cardioid, you know that A and B have to be the same, and you have a radius of, or how, for lack of a better word, radius of 6, right? So think about two numbers that have to add up to be 6, and they have to be the same because you have a cardioid. So I'll let you do that. And then here's where you would just explore, animate, play around with the graphs here. And then we notice that this is actually when you have a sine graph, right? So when you have a sine graph, how do A and B affect what's going on, right? So again, what does A control? What does B control? And then can we write an equation for this sine graph? Now this is a sine graph, right? We know because it has symmetry about pi over 2, right? And we see that from the center, it has a radius of 3, and the length of the loop is 1, right? So we have to have R equals A plus B sine theta, right? And we know that A plus B has to equal 3, but it can only have a difference of 1, right? So what we might want to try is two numbers that add up to 3, but only have a difference of 1. I think that we can just do 1 and 2, right? So I'd say this is 1 plus 2 sine of theta, and we're going to call that a day. 1 plus 2, right? Because again, because there's a loop, the A has to be less than B. All right, so I'll let you try that one out. Rule for when you observe in your a loop in your heart graph, A has to be less than B. All right, so here you can play around a little bit with the graphs. So now we've done circles, roses, and limacons, and a special kind of limacon called a cardioid, right? So last thing you would do is go to this link to do the check for understanding. So just in summary, we've recognized 3 types of polar curves: circles, roses, limacons. We know how the numbers in the equation affect the properties of the graphs. We can write the graph of an equation of a polar curve from its graph, and we can describe properties of polar curves. All right, so do a great job on that CFU. Thank you so much for watching, and I will see you next time.